All right, I think we're ready. All right, and then maybe the lights on that one. There you go. All right, that'll work. And can we shut the door? Hey, you're just like the doorman over there, sorry. So the idea of the limits at infinity and has something to do with, there are two types, right? We start with infinite limits, and those are where we're actually we're getting infinity as an answer. And so the examples I gave you, like 1 over x squared, right? And x went to 0, went to infinity. Here's some other examples I went through. I'm not going to do the same ones. But anywhere where we had a function that took off to infinity from either side as we did a limit, that corresponds to a vertical asymptote. So now when someone asks you to find vertical asymptotes of a function, you know that you're looking for places where you get 0 in the denominator. And that's going to kind of key you off to where that could happen. So I'm trying to get where we can do some examples here. Okay, the other idea was the limits at infinity where you let x go to infinity. So that's a much different prospect. So let's go ahead and do a couple. I'm going to do some examples here, and they're going to be similar to problems out of your book, so that when you do your homework, you'll have some idea of what's being asked. Come on. Here we go. All right, let's find the limit as x approaches 4 of x over, well, let's say 4 from the right. Did I just say right? I meant left. X over x minus 4. Let's find this limit. So let's do what we did last time, which was like a direct substitution, right? We try and substitute, we see what happens. So with direct, what does the numerator become if we replace x with 4? Careful, not 0 over 0. 4 over 0. And that is, again, a bad situation. What we dealt with last class was 0 over 0, right? And we said when we had 0 over 0, we had to do some algebra, right? But whenever we see something like this, where we have like a number over 0, we're guaranteed to have one of 3 answers. Anyone know what they are? Does not exist, or negative infinity, or positive infinity. Did I say that in the video? Do you remember me saying that? Anytime you have a number over 0, there are 3 possible answers that you could get in a limit. You could get does not exist, you could get positive infinity or negative infinity. So for us, what we need to do is investigate this limit a little bit more to figure out which of these it is. Now, good thing for us is that we know which way we're approaching 4, right? We're approaching 4 from the left-hand side. So what I'm going to do to kind of help me see what's happening without having to graph this function is just draw a number line and place the number 4 on that number line, and just imagine that I'm coming in from the left side like this. We already know that the top is headed to 4, right? And we know that the bottom is headed towards 0. The top is a positive number. Agreed? So not only do I know it's a number, it's a positive number. The bottom is headed towards 0. The question I'm going to ask myself is it headed towards 0 through positive numbers or negative numbers? And is it possible for me to determine that? So remember you had suggested, right, Jose, you had suggested that we do that table that one time. We'd like fill out values. And I said, yeah, but we could do algebra. This is actually one where the table idea is almost better. But we don't necessarily need a table. We're going to just pick a number. Somebody pick something that's really close to 4 right here. 3.9, let's say 9. Then you can go 999 or 9999, however many you want. And that would be a number close to 4 on the left-hand side. All I'm going to do is use that number right here in x minus 4 to determine whether or not it's positive or negative. So what would 3.99 minus 4 be? A positive or a negative? Negative. It'd be negative. So I know that the top is headed towards 4, which is a positive number. I know the bottom is headed towards 0, but I just said that it's headed towards 0 through what? Little positive numbers, right? So I'm going to put a little plus on here. Now don't confuse that with left and right. That just means this number is getting close to 0, but it's a positive number. Does that make sense or not? Did I just say, what did we say? 3.99 minus 4, I said that's a positive number.
No, you said negative.
I said negative, but I wrote positive. Okay, it's negative. That's why I'm glad. I could tell from looking at you that something was wrong. All right, so these are little negative numbers, right? Yes? All right. So when we had our first class, I was talking to you about we need to get our head around this idea of infinity, and when this gets big and this gets small, like how things are related to each other. If your numerator is fixed, right, at 4, and your denominator gets smaller, the fraction gets what? Bigger, right? It gets bigger. If the numerator is a positive number and the bottom is a small negative number, that ratio must be negative. Right? Positive over negative would be negative. So it's a huge negative number, which would be negative infinity. Do you all see that? It's just kind of a process of elimination, I guess. No? Yes? You good? Well, I mean, just got to ask. I'm going to do another example. Maybe it'll help. But the answer to this, okay, our answer just by looking at this would be negative infinity. Let's do the same problem. I'm going to change it by coming in on the right side of 4 instead and see if it changes the answer. So let's do it again, rewrite it. Now put a plus here, and we start the whole thing over. What you noticed about the first example here today is that I didn't do any algebra, right? I didn't have to factor and conjugate, all that. This is a different animal, all right? We're approaching this by just thinking through what's happening. First thing we do is a direct substitution. Again, we get the same exact thing, right? We get 4 on top, we get 0. So that right away tells me that there's 3 possible answers. Because anytime I have a fixed number over something that gets smaller, it's going to be one of those 3. Does not exist infinity or negative infinity. So which one is it? So what do I have to figure out? Let's see if anyone, Arturo? No? I'm trying to help you by asking you, when you see this, you know it's one of the 3 possibilities, right? What is it that you need to determine in the ratio? Like what did I determine in the last one? That the top was what and the bottom was what? One was positive and one was negative, right? Which is I was able to nail down negative infinity that way. So once you know this is happening, you have 3 possibilities. Just a matter of determining what's happening in the top and bottom now, positive or negative. All right? The top's easy. Yes? 4 is positive. There's no way around that. So you're headed to a number on top. You're headed to 0 on the bottom. The number on top is positive in this case. The number on the bottom is 0. Just figure out if it's positive or negative. If it's positive, the answer is positive infinity. If it's negative, the answer is negative infinity. That's it. Understand?
Yes.
Are y'all twins?
Yes.
Oh, shit, I just realized that. I was freaking out. I was like, Arturo, what happened? You moved. Okay. Cool. Who's older? By how much?
Like 15 minutes, I think.
Really? Okay.
Yeah.
My wife's a twin. That's why I asked. They're always like, oh, I'm older than you. And okay, this time we're approaching 4 from the right. Okay, we're approaching 4 from the right. That's going to change things a little bit because the number we're going to plug in, right, needs to be to the right of that. So something like 4.001, something like that would work. And so when I mentally just plug that in right here, if I take away 4 from that, it leaves me with a little tiny positive number, doesn't it? 0.001. And the closer I get, I'm always going to have a little tiny positive number left over. So this is approaching 0, but through positive values instead of negative. So this is a little plus, and now I have a ratio that's positive over positive. So the answer to this is positive infinity. See the difference? Coming in on different sides.
So is that going to be the same? So just because we know that there's a plus next to the 4, that we know it's going to be a positive infinity?
I'm glad you asked. No. I'll give you an example where it doesn't work that way. Yes?
So what he just asked is like if there's a negative sign in front of the 4? Or like what happens when you have a negative number up on the top in that case?
Okay, let's just say this problem would have been, to make it, to answer your question, let's just say this would have been like x minus 10. Okay? Then plug in 4 and you would get what? 4 minus 10, negative 6. So this would now be a negative 6, wouldn't it? So I have a number on top, but I know that that number is negative, right? The bottom is still going to 0. The bottom is still going to be a positive number. Now the answer would be negative infinity.
Okay.
Even though, what was your name? Cody. Sorry, I couldn't see it. Cody. Even though you have a plus here, it is possible to get a negative infinity to come out. I think you were saying, is this the indicator of the infinity? Was that what you were saying or no? Yeah, it's not, unfortunately. Okay, so I want to go back. I don't want to erase this yet, but I want to just see if you can tell me what would happen if I asked this problem and I didn't put plus or minus there. It would be does not exist. Why? You would check from both sides. You would have to check from both sides, and you would get positive infinity in one case, negative infinity in the other case, right? Positive infinity in this case, negative infinity in the other, and those aren't the same, right? Positive infinity, negative infinity. So in order for a limit to exist at a point, it has to be the same from both sides. Yes? Okay. So that would be DNE done. So you might be asking yourself, like, how do I show my work during a test, right? Like, how do I show my work on this? This is kind of what I would want to see. That you're looking at the ratio, you're saying, okay, I've got a number over 0. I know that that's going to be one of 3 possibilities. And you could even list this. Like, as soon as you see this, you could say this, or does not exist, right? Like, somehow let me know you know what it means. You know what you need now, right? Then just find the ratio. Use a little number line. Draw it in there. You're good? Okay, let's do another one that's a little more tricky. Okay, let's go limit. Let's change this to a -5. And let's not tell you which side to approach from. And let's go x minus 5 over x plus 5 squared. I'm going to let you do that. Just going to go grab some water while you consider that. All right, where's the numerator headed? It's headed where? Negative 10. So if we do direct substitution here, we're getting negative 10 on top, and on the bottom we're getting 0. And so we're getting a number on top, we're getting 0 on the bottom, so automatically I know there's 3 possibilities, right? It's either this, or this, or this. Now, can we determine the signs of what are happening? So the top is going to a number, it's negative 10, so I know it's a negative number on top, right? What about the bottom?
There's no indication of which way it's
It's 0, right? But which, is it positive or negative? Do I need to draw a number line here? Yeah? Or do I?
No, not really.
It's coming from both sides. Does that mean it's going to be different?
It does not exist.
Does not exist.
The denominator comes out to be, since you're squaring it, it's always going to be positive.
There it is. That's the key. Look, because of the way this problem is written, I do agree that here's negative 5. What if I come in from the left? First of all, someone give me a number that's over here.
5.01.
Negative 5.01. Something to the coming in on the right. Negative 4.99, right? So let's first all agree that if I plug in negative 5.01 right here, this would be, what, a negative number? Very small negative number? But what are you going to do now? Square. So now it's positive. Now if I come in on this side, I plug in negative 4.99 right in here, I get a very small number, right? And it's positive. And then what do I do with it? I square it so it's still positive. So even though coming in on different sides makes a difference here as far as the positive and negative, that squaring kills off the problem and forces the bottom to be positive, which means that you don't really even have to do any of that work with the number line if you just realize that that squared forces this 0 to always be a positive number. And so what's your answer? Negative infinity. It's negative over positive. Right? A negative number over a positive. Did that one make sense? So there's a little bit of things involved. You have to really kind of think through this. Yes?
Is that for any exponent?
It wouldn't have worked for cube.
Well, that's why I said even exponent.
It would have been, oh, I didn't hear you say even. Yes, that would have worked for any even. Uh-huh.
It would be the opposite for odd exponent.
If it were odd, this one would not have existed. Because then if we came in on one direction, like let's just say again, if that was cubed, then if we came in over here, this would be a little negative number. We cube it, it would still be negative. But if we came in this direction, it would be a little positive number. We cube it, it would be positive. So one way it's negative, one's positive. It would be DNE. Mm-hmm.
Does that prove that the limit exists at negative 5, at negative infinity?
That proves that if you draw this graph, if you were to graph this on a graphing calculator, that I can tell you that when I graph it, you're going to have a vertical asymptote at negative 5, and the function is going to dive down to negative infinity on both sides. That's what it'll look like when I graph it. Is that what you were asking?
Yeah.
Yep, that's exactly what it's saying is going to happen. The DNE is when we have something like this happening. So diving down to negative infinity from one side, positive infinity on the other. That would be a DNE. All right, so we'll look at one that's a little more complicated. That's an interesting one. Limit t goes to 2 t squared minus 4 over t cubed minus 8. Okay, direct substitution first. Okay, we get what? 0 over 0. All right. So is this a case where I'm going to say, okay, I've got the 3 possibilities? No. So we got to be careful when we're looking at limits. Like, it was only when we had a number over 0 that we had the 3 possibilities. If we get 0 over 0, what do we have to do? Try some algebra or some trick. Do you have any algebra that's going to work here? Factor? Okay. Difference of squares on top, t plus 2, t minus 2. And difference of cubes on the bottom. There's a formula for difference of cubes.
This one's going to be like, isn't it t minus 2?
T minus 2.
Times t squared plus 2t plus 4.
Good. Who was that? Good. Did you read it or you know it?
I know it.
You know it? Good. Awesome. Very good. I don't run into a lot of students that know the difference of cubes formula by heart. That's a good thing.
Yeah, it's not used often.
It's not used that often, that's why. But it's by the time you get to like more engineering and stuff, it needs to just be. I didn't have it memorized, and eventually I did. You know. So this is a good factoring because the t minus 2's cancel. And then now that the cancellation happens, you try your direct substitution again, and what happens on top? You get 4 on top, and then on the bottom, 4 plus 4 plus 4, 12. So this is 1/3. So just, I wanted to throw one in there that has nothing to do with what I started with to just keep us on our toes. I mean, you have to look at what you have here, right? And we're done. Let's try another one. Limit t goes to 0 of cosine t plus 1 over sine t. So bring in the trig function in now. And let's approach 0 from a side. Let's go from the left side of 0. It would be, direct substitution is going to give us what? Cosine of 0 is 1, right? 1 plus 1 is 2, 2 on top. Sine of 0 is 0. So we have a number over 0. That means we're going to have 3 possible answers. And now it's just determining the signs of those. So can you tell me about the numerator? It's positive, right? Positive 2. So that's a positive number on top. We know this is 0.
We can draw the number line and put 0 on it, right?
Yes, you could. Let me see what happens here. That's what we've been doing, right? We put the number line, we put 0, and we're coming in from the left side. So -0.001. Here's where we run into a little bit of an issue. Before, when we picked this number, wasn't it very easy to just plug it in and see what was happening? Yes? This is a little different because we need to take sine of that number. Agreed? So do we know what sine of that number is without our calculator? You probably do, but don't realize you do. What does the sine curve look like?
Well, all splits between.
It starts at 0, right? So if I'm at 0, I'm at 0, right? Which is what I'm saying here. Sine of 0 is 0, so that's where I am. And I can imagine this as being like my axis, my t-axis. And I'm coming in on the left-hand side of it, aren't I? So I'm plugging in a value that's a little left of 0. What is sine of a value a little left of 0? Negative, because it's below the x-axis. So I know that sine of this number is negative because of the graph.
It doesn't exist.
What wouldn't exist?
The limit.
No, would it be negative infinity?
It'll be negative infinity. It's because we're only coming in from one side.
Oh, okay.
Yeah,
I see that.
yeah, I added it at the end. Sorry, you may have looked down or something. Yeah, so if I only come from this side, does everyone see the difference between this one and the previous one? It's not as simple plugging that in. You actually have to kind of investigate what does sine look like. Well, you're coming in, this is your number line. You're on the sine function, which means you're below the x-axis, which means it's a negative number. So that means this is a negative number, which means you have negative infinity. Now, what would have happened had I not put that negative up here? It would have been does not exist, because you would have had from the left, it would have been a little negative number, but then when we come from the right, it would be a little positive number. And then it would be different from both sides. Questions? Comments? Concerns? All right, now that's kind of this is the examples here of infinite limits. So this is the first part of this section, 1.6, where what we were having was we were having functions that had infinity happening, where one side would go up, the other side would go down, or they both go up or they both go down, something like that. The second part of this section has to do with changing to the idea of, instead of letting x approach a number, letting x approach infinity. And that's what we call limits at infinity. Where is it? Limits at infinity, right here. We're letting x go to infinity. Well, infinity is not a number, right? So when we say we're letting x go to infinity, we're saying we're letting x get arbitrarily large, larger and larger and larger and larger. So let's just take an example, and this is like something that's in the notes. If I do this, what happens? The ratio gets closer to 0. Because what you have is a fixed number on top, right? So basically you have a number on top, and the bottom is becoming infinite. So the number on top's not moving. The bottom's getting bigger, the ratio gets smaller. So that would go to 0. And there's no real other thought that we have to put into that. How about if we do something a little different and we let it go to negative infinity instead? It would also be 0 if I use the same function, right? Because now I have a number. This is going to negative infinity. Does it matter that I change this to a big negative number? No, the ratio is still going to get smaller and smaller. It might be negative, little tiny negative numbers, but it's going to 0. It's squashing it down to nothing. Does anything change if I change it to maybe like 1 over x squared?
No.
It's the same thing, isn't it? You have a number on top. You have basically a huge number that you're squaring, which makes it even bigger, even faster. But we already talked about this. Infinity squared is still infinity. So you have still the concept of a number over infinity, and that's going to go to 0. And so in the notes, this is something I state in the notes, that it turns out that if you take, where is it? Here we go. For any positive number, for any positive integer n, 1 over x to the n is 0. Or, so if you let x go to infinity or negative infinity. So it doesn't matter if this power is 1 on the x, or 2, or 3, or 4, or 5, or 6. Doesn't matter. This, they will always go to 0. But I say positive integers. Why do I not say negative integers? Yeah, because if I put here like 1 over x to the negative 2, that would really mean x squared on top, wouldn't it? And then that would blow up and become infinite, right? You wouldn't get that squashing down effect. All right. Now, I have a handout for you. It starts at the beginning of calculus. If this is your first time seeing it, it kind of gets to be a little bit of an issue trying to remember all these things. So I put together what I refer to as like a limit summary. It's just something you can go off of to kind of help you while you're studying, while you're doing your homework. I don't want you to become dependent on this, so I don't want you to be able to use this like on a test or on quizzes, but this is just to help you while you're getting started, all right? To remember these sorts of things.
Thank you.
There you go. Did we get enough there? No? Here we go. There you go.
We go.
You got plenty more? Need one more over here? There we go. All right, so let's take a look at this. I want everyone to first, I want to put like a big asterisk disclaimer on this whole thing, all right? In this sheet, everything here is when you take a limit. I am not telling anybody here that 0 over 0 makes any sense. Like 0 over 0 is undefined. It is undefined, period. There's no way around that. But if you take a limit, let's say as x approaches 2, of x minus 2 over x squared minus 4, then as x gets closer to 2, this gets closer to what? 0 over 0. And then we could actually do some work on this and actually show that this turns out to be 1/4. So everything in here is what's happening when you're in a limit. Understand? Okay. Now let's look through this. What I have here is the form of the limit on the left side and then the technique used to solve it on the right side. So take a look at the top left box. It says here, if you have a limit that looks like 0 over 0, and then what? Infinity over infinity, or 0 times infinity, or infinity minus infinity, or 1 to the infinity, or 0 to the 0, or infinity to the 0, any of those forms, then you're going to have to use some algebra or some trick. We've only looked at one of those, haven't we? 0 over 0. It's the only one we've looked at. We will look at all of those. We will see all of those, all right? So just, it's coming, just wait. All right, the next one. If you have in the limit something where the top is going to 0 and the bottom is going to a fixed number. So the top is headed towards 0, the bottom is headed to a number, the answer is just going to be 0. There's nothing for you to do. An example of this would be limit x goes to 2, x minus 2 over x plus 3. The top goes to what? 0. The bottom goes to 5. 0 over 5 is 0. Okay, there's nothing to do there. No work needs to be done. The next one says if you go to positive or negative infinity over a fixed number, that your answer is going to be positive or negative infinity. So I'll give you an example of this. How about limit x goes to infinity of x squared over 4. So you take, something gets really big, you square it, it gets what? Huge, divided by 4? Still infinite, right? So this is infinity. there's no work to be done here, is what I'm getting at. So the fourth box down is what we were just talking about right there. If you have a fixed number over positive or negative infinity, it goes to 0. So those are the examples that I was talking about here, like 1 over x squared, 1 over x cubed. If the bottom gets big, positive or negative, it doesn't matter, and the top is stuck, then you get 0. What's the 1, 2, 3, 4? What's the fifth box down? Isn't that what I was doing to start class?
Yeah.
Right? If you have a fixed number on top and 0 on the bottom, you're going to get one of 3 possible answers. Infinity, negative infinity, or does not exist. What do you have to do in order to figure it out? Investigate the behavior of both the numerator and denominator, use a number line. So that's to remind you of how to go about that. And then the last one, bounded over infinity, has a lot to do with this one. But instead of saying number on top, I'm saying what? Bounded. So I'd like to give you an example of that. What is the limit as x goes to infinity of sine x over x? Ah, I'm glad you said that.
Well, no, because it has to be like going towards 0. not-
That's right, okay? So last class I said there was 2 formulas, or we used it last class, but the class before I think is when I mentioned it the first time. I said everyone needs to remember this formula. The formula was limit, x goes to 0, sine x over x equals 1. Remember? And I said, in fact, you can even look at this as being sine of junk over junk. That'll go to 1 as long as the junk goes to 0, right? That's what I said. What's the difference between this and this? Infinity. The junk's going to infinity, right? So the answer is not going to be 1. Right? It's not going to be 1. All right, so try and do direct substitution. What's sine of infinity? No, can't say infinity. What's sine of infinity? Where's your name thing? Where's your name thing? Oh, you got it? Okay. Okay. I was going to call on you, Brandon, because you look like you need to be kind of pepped up a little bit right now. All right? Any idea what happens to this as I let x go to infinity?
Doesn't exist.
Let's see. What's that? I'm saying if x goes to infinity, what's sine of infinity? If that, does it even make sense? What do you think? No? You don't think it exists? So, any logic as to why? Anybody want to help? No?
So, if your x value is approaching infinity,
Okay, so start drawing the sine function, right? And then go out to where? Infinity?
it's going.
Okay, is it getting closer to anything? It's not approaching any one particular number. So you can't say it's headed to 0 or 1, because if you say it's headed to 0, then it goes up again, right? And then it comes back down, and so you can never really get to the end, but it never heads to one particular value. So the numerator actually doesn't head anywhere. The limit of that one doesn't exist, right? It just doesn't exist. Over what? The bottom's headed where? Infinity. But as soon as you see that it does not exist, that's a problem. So that's where that last formula comes into play. This is where that last one comes into play. Because the last one says, look, if your numerator is bounded, now what do we mean by bounded? Stuck between 2 values, and the denominator is blowing up, it's going to force it to be 0. And here's another way I can show it to you that I think would make more sense in this particular problem. Anybody remember in pre-cal when we define the sine function, we had something like this. Like the basic sine function was defined this way, where A was the amplitude of the sine curve. So the number in front of the sine is how big it is, like how big your wave is. And then the B and the C somehow shift and adjust your period and all that, right? Phase shifts. But this number in front always dictates how high the wave is, right? Okay, so I'm going to rewrite this limit as that x, I'm going to write it as 1 over x in front of the sine function. Do you agree that that's the same that as this? Yes. So you could look at this 1 over x as almost being like the a, right? What does 1 over x do as you go to infinity? It gets smaller. So really what's happening is this. The graph of this starts out like a normal sine curve, but gets smaller and smaller amplitude as you go. So it goes like this. See what I'm saying? And so even though it's still oscillating, and it is going above and below 0 and crossing through, those amplitudes are getting shorter and shorter and shorter. Hey, come on in. What's up?
I think I forgot my laptop.
Your laptop?
Yeah, I think so. I was charging on the wall.
Oh,
Yeah, sir.
wow.
Yeah, I know.
You just think those guys right there.
Sorry about that.
Oh, that's all right. So the amplitude, even though it's going back and forth, is it headed towards something? It is. It is falling into a window. See, every time you move out, like let's say it's within that little window right here, right? Back here it was within a larger window. Back here it was within an even bigger window, right? What's happening to that window as you continue? That window is getting smaller and smaller and smaller, and that window is approaching what? 0. And so the function's value is approaching 0. It's kind of a weird limit because it still does get above and below the x-axis. It's just that window keeps narrowing down. Another way to look at it, I don't want to bore you with this, but another way to look at it is this. If you look at 1 over x, just the graph of 1 over x, it looks like this. That's what 1 over, it's supposed to get asymptotically closer, right? That's 1 over x. And if you reflect it over the x-axis, like this is what it would look like. And so if you graph this function, 1 over x times sine x, what it is a sine curve that has to be trapped between that funnel. And so if that funnel is going to 0, then so is the sine curve. So is that sine curve. Now, why is something like this important? Think about, we use sine functions to model things, right? Periodic behavior. But like if I take a ball and I bounce it, right? It doesn't bounce and then come all the way back up to where I let it go from, right? And then bounce and come all the way back up and bounce and come all the way back up. What happens? Bounces, comes up, not as high. Bounce again, not as high, not as high, not as high, not as high. And then eventually what? And it comes to rest. Or does it? Or is it actually still oscillating? At the atomic level, it's still vibrating. But I'm just saying we could model it to a certain extent, right? At some point, we have to kind of wave our hands at it. But this is a good model of that behavior. It's the periodic thing we need with a smaller and smaller amplitude as we go, right? That's better than a sine curve to model a ball bouncing or a spring, right? All right, so we need to know how these things behave.
Does that only happen with true functions?
No, there's a whole group of different types of periodic functions. So sine and cosine are obviously the ones that we like. Yeah. All right, so let's look at another couple of infinite limits. Some classic sort of examples, something like this. Direct substitution first. Direct substitution first. And we have a pretty good question to ask ourselves right now. What happens to the top? Okay, I agree that this first term goes to infinity, right? Infinity squared times 3, that's infinity. But then what? Minus infinity plus 5. So infinity minus infinity plus 5, something like that. The 5 doesn't matter, does it? 5 is finite. Compared to infinity, 5 is negligible. So who cares about that? What's infinity minus infinity, though?
Would it matter since the first infinity is squared?
Okay, first of all, infinity minus infinity, we don't know, okay? We don't know in general, we talked about this in the very beginning. Infinity minus infinity is not something we can easily answer. But in this particular problem, the leading term here is squared. This one is what? First power? And that means you have a quadratic term and you have a linear term. Which one is going to overpower the other one? The quadratic term is going to overpower the linear one. Yes? But I have an even better way to show you, to prove that to you, if you don't like that. Forget the 5, because remember, we said that doesn't really matter, does it? Just look at this real quick. If I pull an x out, do you agree with that? Just out of the first two. Now let x go to infinity. What is this? Infinity? What's 3 times infinity? Infinity minus 4? That's still infinite. What's infinity times infinity? Infinity. Now, you don't need to show any of that. In this class, it's okay. If you have a quadratic function, you know that the leading term is going to control everything. So this top is going to infinity. All right, infinity. Over. Same exact sort of thing. Infinity over infinity. And now you have the second type of form on this top left box. We had 0 over 0, right? Now we have infinity over infinity. And when we have infinity over infinity, we don't know. We need to do some algebra or some sort of trick. It's not 1, right? This is not equal to 1. We have to figure out what's going on. So the question is like, does one of these, does the numerator dominate the denominator, or is it the other way around, or do they just kind of like make peace with each other and say, you know, we'll compromise on something? You may have learned, some of you probably learned in college algebra that this is part of what's called a rational function, and that all you have to do is look at this number and this number and do 3 over 5 if those are the same powers. Y'all learn that? That's what happens. We call those the horizontal asymptotes. It's what happens at the ends of the function, which is exactly what we mean when we say what happens when we go to infinity or negative infinity, right? Isn't that the same exact sort of thing? Left and right side? But we're not in college algebra. We're calculus students now, so we want to be able to analyze a function better than this. And I'm going to give you an example right after this that your college algebra technique will fail on. So here's the standard technique, the standard trick, the standard sort of method to approach this. You all paying attention? Okay, here it is. What you want to do is use the power of this thing that we just determined a second ago, that this goes to 0 when x goes to infinity, right? When x goes to infinity, we know that x to a positive power, that'll squash down to nothing, right? If I put limit out here, x goes to infinity of this, it'll be equal to 0. I'm going to use that in the problem. But that means I need to create this ratio somewhere. So I'm going to create it, and the way I'll do it is I will find the highest power of x in the denominator. The highest power of x in the denominator. And that's what's going to force me or tell me what I'm now going to come in here with to make this nice thing happen. I'm going to leave some space in the front. I'm going to come in and hit this thing with a number 1. The number 1 is a great thing in mathematics, right? It can be anything we want it to be, the number 1. So x squared is the highest power of x that I see. So what I'm going to do is I'm going to come in here and multiply by 1. The 1 that I'm going to use is 1 over x squared times 1 over x squared. Again, the x squared is coming from that x squared right there. Now, when I do this, Let's think about what's going to happen on the bottom. When you multiply this 1 over x squared through to each one of these, right? What's the first one going to become? Just 5. What is the next one going to become? 1 over x, right? 1 over x. What is the next one going to become? 1 over x squared. Same thing, right? And so I know guaranteed that if I do this, the denominator is going to be a 5, a 1 over x, and a 1 over x squared. And if I let x go to infinity, the 5 will stay there. This next one, 1 over x, will go to 0. The next one, 1 over x squared, will go to 0. And I'll be left with a 5 on the bottom. And that sure is a lot better than having an infinity on the bottom or a 0 on the bottom. Now, what happens on the top, I'm just going to have to wait to see. All right? Does everyone at least understand where this is coming from? Where I'm pulling that from? Yeah? All right, go ahead and multiply through. And do the same thing on top. And you'll get limit x goes to infinity. You've got what on top there? 3 minus 4 over x plus 5 over x squared. Good. And then bottom we said would be 5 plus 1 over x plus 1 over x squared. I am trusting that everyone can distribute that through and clean it up. So now take the limit. When I take the limit, at this point I'm not going to write limit anymore. The top, the 3 stays. What did this one go to? 0, so minus 0. This one went also to 0. Over 5 plus, 0 plus 0 again, and the answer is 3/5, which is just exactly what they told you in college algebra, right? And that's why it always worked in college algebra. If these were the same powers, right? If these are the same powers, and I'm going to pick this power to come in with, then I'm going to be left with the coefficient here and the coefficient there, right? That's what I'm going to be left with all the time. And so that'll always create that situation where those 2 numbers in front drop out. Okay. Questions?
You got the 1 over x squared again now?
By looking at the denominator at the highest power of x, which was x squared, and saying, I need to get rid of that x squared, so I'm going to divide it by x squared. Division by x squared is the same as multiplying by 1 over x squared. So you see this first multiplication here to here. I have 1 over x squared times 5x squared, and the x squareds will cancel and leave me with a 5. So if this would have been x cubed, I would have come in with 1 over x cubed, 1 over x cubed. If it would have been x to the 7th, I would have been 1 over x to the 7th, 1 over the x to the 7th. But it's the highest power that you see down there.
So it could be like, if it's 5x cubed, then we'd use that.
1 over x cubed. Yes?
You said you would use the highest one, so if it was like 3x to the 6th, and on the bottom it would be 5x to the 8th, and you would use x to the 8th?
That's right.
On top and bottom?
Yep.
Okay.
Yep. You're looking at the denominator. And the reason why is because you want the first term, or the highest power here, you want it to go away so that you have a number. Okay? And that number, hopefully, after you do all this stuff, if you know you're going to have a number down here, you know you're not going to have 0 down there. You see what I'm saying? Yeah, or infinity. So you're trying to avoid the possibility of the denominator being messed up. Now, it doesn't always work nice, as you'll see now. Sometimes you run into problems. Like this one. So look, I think I've said something like this before, but maybe you're getting more of an appreciation for it. now that we're doing this. Calculus is very different than pre-cal in college algebra in the sense that in pre-cal and college algebra, a lot of it was like monkey see, monkey do. Like this is a quadratic, here's how you find the vertex, and it's very much formula driven and just, you know what I'm saying? Like this, I can give you millions of problems and then give you another one you've never seen something like that. They're all different. It's really number sense, understanding how things affect each other and behave. So it's much deeper than just me giving you some things and now you just go repeat that now. Yeah? I can give you basic ideas of how to approach it. I can remind you of algebra that you need, but at the end of it, you have to really feel confident about how things behave. Functional behavior is different than just trying to graph a sine curve. Tell me what's happening if I try direct substitution. Top's going to infinity. The bottom is, well, inside here we know that that's becoming infinite. And then the square root of infinity is still infinity, right? We talked about that. So we have infinity over infinity. That's one of the forms we don't know. We have to do something about it, right? So then someone's like, wait, hold on. Last class, square root conjugate, right? You're thinking, because that's what I got you thinking last class. But the conjugate's not going to work in this case, all right? It's not. What's that?
It'd be the same thing. It'd be like, nothing would change underneath the square root. If you're trying to do that, right?
Well, it would, first of all, to do conjugate, I have to have square root of something plus or minus some number or something like that, or some other root or something. This is all one root. So the conjugate of that doesn't really exist because it's a single expression. But I'm just thinking, like, you start to get to a point where you're like trying to get your head around all this, so you start seeing things, you're like, that's what I'm doing, and then you wind up getting lost. So, all right, so what did I say to do when we had infinity over infinity? I said one of the things you can try is to identify the highest power of x in the denominator, and then come in with 1 over that, right, on the top and bottom. So what would be the highest power of x? Right here, right? Here's the trouble, though. That x squared's trapped, right? It's trapped under a root. So the question becomes, if you're going to come in here with the 1 over x squared out here, you have to do it on top and bottom, right? Because it has to be a 1. How are you going to get it in there? How are you going to get it into the square root?
Could you get rid of the square root?
You can't, because there's addition here. And you can't square the whole thing because then you're squaring the problem. It needs to be an equation to square everything.
You can't rationalize the denominator?
It's still, well, you could, but then you'd have, this would become, you're saying multiply this times itself, right?
Yeah.
And then you put it on top, and then now you have something quadratic in the bottom, but you'll still have a root on top, right? It'll still be a problem. You can try it. It's still going to be a problem if you work through it that way. Because the root on top is still going to create an issue for you.
What if you, how do you say, like, use the letter root and put the 3x to the 1/2, x to the 1/2, and split it.
You can't split it, though. Because it's 2 terms under a root, you cannot split it into 2. This goes back to the whole idea of something like this. What's the square root of 4 plus 9? If you split this into 2 roots, you're saying that the answer should be 2 plus 3, right?
Yeah.
Which would be 5. Is the square root of 13 5? No. This is definitely a violation of algebra here. That's always a good way to check things. If you have an intuition of, yeah, I'm going to try and split, just try something. And if it doesn't work, that means you can't do that. I did this all the time when I was a student at your level. There were so many rules I wasn't sure of. And this is always the way I always checked it. And if it failed once, I was happy. If it worked, I'd be like, I better try like 5 or 6 more to make sure it works.
So what about if you write the square root as an exponent?
So the whole thing to the 1/2, you still can't get anything past it.